Okay, we got a snow problem. Kind of like how we started out. Let R of t be the rate function that measures the rate at which snow falls in inches per hour. Somebody tell me something about this snowfall. Characterize it for me. What's happening with this snowfall? Yeah, each hour, like the storm's picking up. Would everybody agree? The storm's picking up. And in fact, if you were to graph this, so I'm just going to do I'm not going to do a real accurate graph. But would everybody agree that that's kind of the graph? Okay, so notice what it says. It says consider the concavity of RT. Is this concave up or concave down? It's concave up, and that's going to affect our estimate. It says use it to determine an upper and lower bound for the total accumulation over the 6 hours. So I'm going to try to think about how we did this stuff. And things like right-hand sums and left-hand sums, that kind of rings a bell for me. How about you guys? So if I do a right-hand sum, let's just put an interval on this guy. And if I do a right-hand sum, will that end up being an overestimation or under? It'll be an over. So let's come up with an overestimation for the amount of snow by doing a right-hand sum. What's the width of each interval? 1 times the sum of the heights. 0 to 1, 1 to 2, 2 to 3, so on and so forth. So what's the first height I use? 0.1 plus 0.3 plus 0.6, 1.2, 2.4, 4.8, right? There we go. I'm not using my calculator. I'm trying to be super smart here. So we got 6, and 3 is 9. We're going 9.4 out of that guy. Would you agree that 9.4 might be on the high side? And the fact is, the only way we knew that is by kind of sketching the graph a little bit, like thinking about it, and realizing that right hand will, in fact, give us an overestimation. So what's going to give us an underestimation? The left-hand sum. And so if I do the left-hand sum, how do these numbers here change? Yeah, 0.1, 0.3, 0.6, 1.2, 2.4, and then no 4.8. So I end up subtracting off a 4.8 and adding on a 0, right? So if I subtract off 4.8, what's 9.4 minus 4.8? 4.6. So that's the lower estimate. That's the upper estimate. It says let S sub 0 be 2.4. What the heck does that mean? Exactly. S is our position. This is our rate, okay? This is our position. That's our rate. This says that there are currently 2.4 inches of snow on the ground. So it says use T sub 4. What does that mean? So there's a T rhymes with trapezoidal. Trapezoidal, very good. So we're going to use the trapezoidal approximation to approximate snow coverage at 4 hours, okay? So how did we do trapezoidal? Did you remember that? Yeah, we can do the right hand and left hand divide by 2 as long as the widths are the same. And when we do the AP exam stuff later on, when they do these, they make sure the widths are not the same, so you have to use a different formula. But we'll use right hand and left hand right now. So remember that, when we want to know the total amount of snow coverage, really what we're setting up is we take our start, which is 2.4, and we add it to the integral 0 to 4 of R of t dt. I mean, that's what we're doing. That's what we talked about yesterday, didn't we? The deal is that we can't come up with an exact value for this integral because we have a table. So we're going to use R sub 4 and L sub 4 to approximate T sub 4, right? Right-hand sum and left-hand sum to come up with trapezoidal sum. So R sub 4 is going to be equal to, what do we start with? Very good, 0.1 plus 0.3 plus 0.6 plus 1.2. If I add that up, I get 1.8 and 0.4 makes 2.2. And then L sub 4, that's going to be, how does that change? Plus 0.6. So I just subtract, yeah, I get 1 out of that. So if L sub 4 is 1 and R sub 4 is 2.2, how do I figure out T sub 4? Yeah, so it'd be 3.2 divided by 2 is 1.6. And so that means that we've had 1.6 inches of accumulation, but there's already stuff on the ground, so total coverage, we would say 2.4 plus 1.6 is equal to 4 inches of coverage. Yeah, it's like it's getting worse, right? So it says for the next one, it says use the table to approximate R prime of 3 and R prime of 4.5. So yeah, what does that mean? That means is the snowstorm getting worse or is it tapering off? Is it getting worse or is it tapering off? Which one's happening? Yeah, well, how much worse? Because the rate is increasing all the time, isn't it? So I want to estimate R prime of 3. R prime of 3, what does R prime of 3 mean? That means the slope, the derivative, right? Using a table, can you actually find the actual derivative value? No. So we got to rewind the slope. So remember, we have a way of doing that. Suppose that this is 3 right here, and you want to estimate the derivative at that spot. Hopefully you remember we talked about this early in our class. I'm going to pick a point in front of it and a point behind it. And wouldn't you agree that that would be a good approximation? So what's the point in front of it? Right there, right? What's the point behind it? Right there. So what I do is to approximate R prime of 3. R prime of 3 is approximately, and we do R of 4 minus R of 2 over 4 minus 2. I find the slope. That's how we approximate. What is R of 4? 1.2 minus 0.3 divided by 2. So I get 0.9 over dose, which is 0.45. 0.45 what? Inches per hour squared. Is anybody confused how we got inches per hour squared? Like you were wondering, what do we come up with? Here's how you come up with it. How do we measure rate? The rate is inches per hour, right? Well, you take the derivative of r, because this is r prime, right? So it's going to be a rate for that. So inches per hour squared. We want to do r prime of 4.5. Anybody want to guess what points we'll choose if we want to do r prime of 4.5? Yeah, so r of 5 minus r of 4 all over 5 minus 4. Well, what's 5 minus 4? So I get 1 on the bottom. What is r of 5? 2.4 minus 1.2. I get 1.2 inches per hour squared. Hey there, bud. And finally, the last question here, and then we'll move to the back side. It says, what does that thing mean? Does that look familiar to you guys? We learned that the average value of a function is equal to the integral times 1 over b minus a. So can somebody tell me How do we get 1 over 4 out front here? Because 5 minus 1 is 4. Very good. So what this means, 1 over 4 integral 1 to 5 of r of t dt means the average value of what? The average value of what? What function do we have? The average value of the what is this? The average value of the rate of the the average value of the rate of the snowfall. The average value of the rate of the snowfall during what time period? During what time period? What time period are we talking about? Nope. 1 to 5. Time equals 1. Time equals 5. That's what it is. We're going to approximate it. It says use right-hand sum to approximate it. So I have 1 over 4 times, what's the width of each interval? 1 times the sum. What's going to be the right-hand sum from 1 to 5? What's the first number you choose if we're going 1 to 5, right-hand sum? 0.3 plus 0.6 plus what? 1.2 plus. Okay, pause. Don't add it up. Don't add it up. Watch, watch, watch. This is really cool. This is where it should make sense. Folks, I want you to look at it. We're going from 1 to 5. 1 to 5. You're going from right here to right here. Look at those values. 0.1, 0.3, 0.6, 1.2, 2.4. What do you think is the average value? What do you think is the average of these things? What would you say is approximately the average? Just give me a number. 0.6? Any other thoughts? I think it's probably like 1 personally, but I think that the 2.4 is going to weight it out a little bit. Our formula will actually compute that, okay? And it's easy to do. Here's all we do. 0.3 plus 0.6 is 0.9 plus 3.6. So we get 1/4 times what? 4.5. I'm just gonna do a little crazy math here if you guys are okay with it. Just do 1 over 4 times 45 over 10, which is 45 over 40, or 9 over 8, which is 1.125. So yeah, does that make? I mean, if you look back at the data, does it look like maybe about 1 would be about the average? That computes it for us. It finds the average value of a function, which is really neat. Good. All right, flip it over. Last problem. We'll be ready to move on to different stuff. What's different about this example right here? You're given a graph. So we looked at raw equations. We typed them in our calculator. We looked at table. Now we're looking at graph. It says let C prime of T be the line graph below. So this is C prime of T. And let it represent the rate at which customers are being served while purchasing music on an online store. Is anybody actually... Do some research on the answer sometimes. It's a crazy story. All right, so here we go. Says what is an underestimate for the number of customers served over the course of the first 8 minutes, and what is what's an overestimate? What's an underestimate? What's going to give us an underestimate or an overestimate? Excuse me. Is a left-hand sum or right-hand sum going to give us a over? Right-hand sum will give us an overestimate, won't it? So let's quick do a right-hand sum, and this isn't bad at all. We just kind of draw our. What's our width for each? We're just counting each of these as 1. So what's the width of our interval? 1 times The sum of the heights. What's the first height? A half. What's the next height? 1. What's the next height? 3, then 3, then 3, then 3. We have 4 3s in a row, don't we? And after that, plus 4 plus 5. So we got 3 times 3 times 3 times, or 3 plus 3 plus 3 plus 3, so that's 12. And then we've got a 9, that's going to be 21, 22, 22 and a half. Well, 22 customers served. Okay. How do we do a underestimate? The left hand will be an underestimate in this situation, so I've got 1 times. Now, what's going to change in my numbers here? Because I could keep them pretty much the same, but I'm going to pick up what's my first value going to be? 0. And then I lose the 5, right? So it's going to be through 4. So if I simply take 5 off of this, right? That's all it's going to change at. So I'll get 17.5 customers. So would you guys say that 20 would probably be our best estimate? 20? We all agreed there? It says, what is the average rate at which r double prime of t is increasing? This is c prime of t. So it's not asking for the average value of this. It's asking for the average rate of change. How do we compute average rate of change? Slope. Exactly. It's asking for the average rate of change. I can't find instantaneous average rate of change. I got to do with slope. So we're going to figure it out. So we're wondering this guy from here to right here over that entire interval. So you all agree it's going up, right? I mean, over time they're serving customers more quickly, which is good. You know, they're getting better at their jobs. It's a good thing. Well, so what's this coordinate right there? I'm over 8 and up 5. So we have 8 minus 0 over, I'm sorry, 5 minus 0 over 8 minus 0, which is 5 over 8. What? What's our measurement? Customers per what? Minutes squared. Good. So we're getting better. You know, our people are being more efficient. We're getting at the rate of their rate. It's getting better. Kind of like that snowstorm was getting worse, right? We're getting better. And our last question here. Notice how similar these two questions are, right? They both make you think of average, right? But this means the average value of what? The average value of c prime of t. It's the average value of, then let's describe what is c prime of t. What does that mean? What is c prime of t? C prime t is the rate, average value of the rate, customers are being served. This is a learning one for me. So again, I take a ton of these AP exams and to try to make sure I'm prepared for what you guys are going to see. And I've gotten this one wrong about 3-4 times. So I've stopped there. They always want you to talk about the time interval. During the time. During what time? Yeah, time equals 0 to time equals 8. You got to have that. So you want to describe the bounds of the interval. So, you know, this is kind of cool as we figure this out. What as you look here, look at that function. We're wondering the average value of that function, so the average height. I need a volunteer. Shania. Everybody clap for Shania. Yay, Shania. Yeah. Yeah. Would you agree that the average value is not going to be up here, Shania? Would you agree that the average value is not going to be down here? You tell me when you think I'm at the average value. Right there? Here? There. So you're saying right at 3. Everybody see how she kind of just eyeballed that and say, 3? Anybody want to take a stab, say, I think it's higher or lower? You're thinking it's lower. You think it's maybe like, say, 2.5 or something? Well, we can actually figure that out. How do we figure out? We do this integration right here and calculate the exact value, okay? So let's do it. 1 over 8 times, and we can figure this out, no big deal. Can you figure out this exact area? Yeah, it's not that bad. What's that area right there? Yeah, 1, because it's a triangle, right? 1/2 times the base times the height, so that's 1. So we're going to gather that 1 down here. No plus, no comma. Let's do some more. I'm going to just start counting a bunch of squares. Are you okay with that? So you actually do this on the AP exam. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I've got 17 there. You good with that? 17 plus, I don't know why I put a comma. Sorry. Yeah, 1 plus. And then how about these two? What are they going to make? They're going to make 1. They're going to make 1 plus, and then what does this bad boy make right here? That's 1, so I've got another 1. So what do we get out of that? 20. So I get 1/8 times 20, which is 20 over 8. What is 20 over 8? 2.5, right? What's our label? 2.5 what? Per minute. Again, we're okay. So hey, let's focus here. Okay, hey, label girl right here. So C prime of t, we're finding the average value of that guy. The average value of that guy. So we're not taking a rate. We're finding the average value of that guy, and we describe that as customers per minute. Now looking back at our estimation right here. Okay, Shania went to 3, a valid option, right? Josie said, hey, I think it's gonna be a little bit lower. Is that right where we're at? Darn right. Why? Because you're extremely intelligent. So way to go. Nice job. We are done with section 5.4. This is the conceptual side of things. We're going to move on to very algebraic stuff. And people, as the stuff we move on to, people tend to really like. Okay? So this worksheet, know this one. Stuff we move on to next, generally pretty good for people. Okay? You don't have a new worksheet yet. No.